Friedel-Crafts acylation, based on the person that first reported it. And we looked at the fact that it works fairly well, but when we have a primary alkyl halide, just like anytime we're going through a carbocation intermediate, we're always going to get the rearrangement. So that's definitely a limitation with this reaction, and we'll talk about other ways to fix this. Other limitations, and there are other major limitations that you're going to need to know, and this is especially going to be important when we talk about synthesis. One is that the halide leaving group must be attached to an sp3 hybridized carbon. So this doesn't work well if it is an sp2 or sp hybridized carbon. That carbocation is just too unstable to form, so we don't see those happening. So we have to have an sp3 carbon. Primary will lead to rearrangements. Tertiary and secondary work really well, but this won't happen on a double bonded carbon or a triple bonded carbon because the carbocation isn't stable enough to form. So that's very similar to our SN1 and SN2 reaction limitations as well. Another limitation is once we add one group, polyalkylation can occur. And sometimes it's hard to stop. We can control that by our amount of Friedel-Crafts acylation we're adding. Concentration can definitely help. We're going to talk about why polyalkylation occurs in the next couple of slides. So we're really going to look at that. But right now, just polyalkylation can occur. You have to be careful. The main limitation that we need to talk about is electron withdrawing groups, with the exception of halogens. Halogens, this reaction can still occur. It's not electron withdrawing enough. But moderate and strong electron withdrawing groups will keep this reaction from occurring. And no reaction is going to occur if something like a nitro group is already on the ring. And that's going to be really important when we are looking at synthesis. So no reaction will happen. Electron withdrawing group pulls electron density from the ring, making it less nucleophilic. And these are just not electrophilic enough, even with our Lewis acid. So they're just not strong enough electrophiles if we have an electron withdrawing group present. And that is a limitation. So we're going to revisit that later when we start talking about synthesis and putting these reactions together. If we don't want to do an acylation, an alkylation, we can also do an acylation. So an acyl group is basically putting on a ketone. Your acyl group is your C double bond O. And then we'll end up with a ketone or an aldehyde at the end. Typically, this is going to be a ketone and not an aldehyde, but technically it could happen with there being a hydrogen. So this reaction is very similar. It is also catalyzed by the Lewis acid. What we need is an acid chloride. So an acid chloride is a carboxylic acid derivative. In chapter 21, we're going to be focusing on it more. It is basically like carboxylic acid, but instead of an OH directly attached to the carbon of the carbon-oxygen double bond, it's a leaving group like chlorine or bromine. The most common what you'll see is chlorine, acid chlorides. Acid bromides can happen, but they're just not used as much. Acid chlorides are the most common. Fluorine would be too reactive. Some acid chlorides are very reactive already, and they will react with water in the atmosphere pretty violently. Some of them are very toxic. You have to be really careful when you're working with them because they're very reactive. We're going to dissect the reactivity of acid chlorides in chapter 21 in a lot of detail. So here we have a leaving group next to a carbon-oxygen double bond, and then what will form is the acylation. Again, we still need a Lewis acid. In this case, AlCl3 is appropriate because we're using fluorine. So we usually try to keep that constant. So this mechanism is very similar. The chlorine of our acid chloride can attack our aluminum, and then that forms an acylium ion. Now this is a carbon with a positive charge, but it's next to not a carbon-carbon double bond, but a carbon-oxygen double bond. We actually do have a resonance structure with this, so that stabilizes it slightly. So typically a carbon on an sp positive charge on an sp2 carbon will not form. But this isn't just an sp2 carbon, it's sp2 carbon here, a carbon oxygen double bond. But that being said, this is still very reactive and very electrophilic. We can force it to form with that Lewis acid, but it's very reactive. It is stabilized by resonance. The oxygen with the positive charge is not very stable, but in this resonance structure, all the atoms have a complete octet. In this resonance structure, carbon does not. So that does stabilize that positive charge a little bit. But it's still very electrophilic. So, also we don't usually get rearrangements because of the resonance. Any other carbon that positive charge would be on, whether it would be more or less substituted, would not be as stable because this one has resonance stabilized. So resonance always wins over induction. So our mechanism, our benzene ring is going to, again, attack our very reactive carbon, pushing electrons onto the oxygen. And then we'll have our sigma complex. I'm not showing the sigma complex, all of the resonance structures here, but we know this carbocation has our resonance structures. And then just like all of our other mechanisms, we reform the group. So now we have a new carbon-carbon bond. We have this acyl group. So what are the uses of this reaction? If you want to put a ketone on your ring, this is a really great reaction. But another really useful reaction for this is, again, if we did the alkylation and we wanted this carbon to be primary, we wouldn't be able to go through this route because that route would give us predominantly this construct. And that's not what we're looking for. So what we can do instead is we can do the acylation, because that will lead to this carbon, and then we can reduce this, and this is a new reduction reaction that we haven't talked about, but what this reaction is reducing with zinc HCl heat, and we do need a very reactive catalyst like mercury to fully reduce the carbon. This isn't reducing to a alcohol, this is fully removing the oxygen, so this plus of course water is formed. Now notice this is very similar to your reduction of your nitro group with zinc and HCl, but this is more reactive. Zinc and HCl will not on its own reduce this, but once we add mercury and a bunch of heat, we're basically pushing a lot of conditions and adding a catalyst, and this will reduce completely. Now we can form this product in a high yield. So if I want you to give me this as my final product, where it's primary, you should give me this route and not this route, because this route is wrong, you will not get this in a high yield. So this is the best route. Now a note, if you do have a nitro group anywhere on the ring, the stronger conditions will reduce it, because if the weaker conditions reduce it, the stronger conditions will also reduce it. So if you don't want to reduce a nitro group, then you can't add it before you do this reduction. So keep that in mind. So if we only wanted to reduce the nitro group, then we wouldn't use mercury and heat. So mercury and heat is very important to this reaction. It catalyzes it and allows it to happen. This is called the Clemmensen reduction. Again, another named reaction. And we're going to visit it a little bit more detail in chapter 20 when we talk about ketones. But basically, we could fully reduce a carbon-oxygen double bond. Polyalkylation does not generally occur with acylation like it did with alkylation. And again, we'll talk about why later in this chapter when we talk about substituents on the ring and how it affects the reaction. So we don't typically get a second addition. So the next thing we're going to talk about is actually going to tie into what we just talked about here with why a second addition doesn't occur very easily. And that's what we call activating groups and deactivating groups. Whoops. There we go. So, let me move over here. Substituted benzenes can actually undergo our electrophilic aromatic substitution reactions faster than non-substituted benzenes. So if we look at toluene, which is our benzene ring with one CH3 group on it, what we see is it actually undergoes nitration 25 times faster than unsubstituted benzene. So we call this an activating group. It is activating the reaction, making the kinetics faster. Remember, when we're talking about kinetics, we're discussing the activation energy, not the difference between our thermodynamics, but just the difference between our reactants and our products. So what we're looking at is a lower activation energy is going to make this reaction faster. Things that can contribute to the reaction being faster are the electrophile being more reactive, but we're using the same electrophile in both cases of our substituted benzene and our non-substituted benzene. So it must be something to do with our substitution of the benzene. Now CH3 is and we're going to come about explaining this in two different ways, both thinking about our starting material and also thinking about the stability of our resulting intermediate carbocation. And they're both in agreement. So both can contribute to why this is an activating group. So substituted benzenes with carbon-containing groups tend to undergo electrophilic aromatic substitution faster. And it has to do with the fact that our CH3 is an electron donating group. So remember, our benzene ring is acting as a nucleophile. So it needs to give up its electrons. If we have a group that is donating electron density to the ring, that allows it to give up its electrons easier, therefore activating the group and bringing down that activation energy. And we're going to look at the activation energy in a second. The other thing to note that's really important when we're discussing activating groups is where the new group is going to end up relative to our activating group. So we do see regioselectivity when we have something like a CH3 group on our ring. So remember, our ortho position is the most close, our meta, and then our para. And what we see is we nearly get zero meta, very little meta, but we get a lot of ortho and a lot of para. To explain this directing, we're going to have to look at our sigma complex. And our sigma complex is going to explain why we get ortho and para directing, and that's what we're going to call it when we have regioselectivity, that our CH3 group is directing the new group onto the ortho or the para position, but not directing in the meta position. So we're going to look at the sigma complex to understand that. To look at the sigma complex, we're going to have to actually look at the three sigma complexes from the reaction of each of these. So we're actually going to be looking at 9 total sigma complexes overall. So 9 total compounds. Because we have to look at the differences in the carbocation in all of those additions. So if we attack in the ortho position, and this is already having our electrophile shown, then what we're going to be left with is the carbocation here, and then here are our sigma complexes. One thing to note is that we have a tertiary carbocation, a secondary, and a secondary. Remember, CH3 group is electron donating, so that makes our tertiary carbocation more stable. So with our ortho attack, we get a more stable tertiary carbocation. If we look at the meta attack, notice that we have the addition occur here. That's going to put the carbocation here. And then to follow our resonance structures, notice that there's no way for the carbocation to be tertiary. So it's not necessarily that having the CH3 group with the meta position, we have any horribly unstable carbocations, but we never get this extra stabilization like we do in meta. In the para position, you'll see that we also have the ability to form that more stable carbocation, the tertiary one, the carbocation that's directly next to the electron donating group. But we never see that in meta. So this is what drives the fact that we have the ortho-para attack. I asked you to explain to me why CH3 group makes ortho and para attack. You have to show me all three of these, because that explains why we don't get very much meta. To really visualize this, we can visualize this in our reaction coordinate diagram. Because the ortho attack has an extra good intermediate, we have a lower activation energy for the ortho position. But the meta never has that carbocation that's tertiary, so it has a higher activation energy. The para also has that lower activation energy, so therefore we have this more stable carbocation and a lower activation energy. And when you compare these three, it makes sense why you're going to mostly get product from these two and not this one, because that's a higher activation energy. Another thing to note is the para attack is slightly lower than ortho. What's causing that? Why is this one a slightly lower activation energy than this one? Sterics. Our NO2 group is further away from our CH3 group. And, yep.
So why, if para has the lowest activation energy, why do you get more ortho?
With the case of CH3, it's a statistical thing. You have two ortho positions and one para. If it's anything bigger than CH3, ethyl, isopropyl, anything bigger than CH3, you're going to mostly get para for major. CH3 is special because it's not as big, so sterics aren't affecting as much, but the bigger that group gets, the less probability of getting ortho. But with CH3, it's purely statistical. It's a 2 position versus a 1 position. So you're going to get more probability just based on statistics. But anything bigger than CH3, you're going to mostly get para attack. CH3 is the only special one where you get a little bit more ortho. And you don't see that in the others, but you get almost no meta. There are stronger activation groups in CH3. So our R groups only stabilize our carbocation through induction. But if we have the possibility of resonance stabilization of that carbocation, remember resonance always ends over induction, we're going to have an extra activating group, or what we call a stronger activating group. So if we look at the methoxy group in anisole, it's actually 400 times more reactive than benzene versus our benzene with the toluene. Toluene was only 25 times more reactive. That's coming from the fact that that oxygen has a lone pair that can form resonance structures with the double bond. So because of that, that makes the ring even more electron rich. Now I know oxygen is electron withdrawing, but it has a lone pair that's in conjugation with the ring. So it's electron withdrawing through induction, but it's electron donating through resonance, and resonance always wins. If we look at this, this is what our resonance structures of our anisole look like, no matter what conditions it's under. So notice that our oxygen can donate electrons into the ring, forming these resonance structures. Now our most stable resonance structure is our neutral one, because carbon doesn't really want a negative charge. But these are still contributing negative charges, contributing resonance structures, and therefore what that means is our ring is more nucleophilic, because a carbon with a negative charge is pretty nucleophilic, which is why it's so much faster, because it's not as stable. But this is also going to affect our directing. Now, because this is so reactive, sometimes you will get poly substitution. For example, with BR2 and FeBr3, you may get, if you don't control your conditions really well, bromine in both ortho and the para position. But no, it's not in the meta position. If we control our conditions, we can get mostly para based on sterics, but you have to be really careful with stronger electron donating groups. But they are ortho-para directors. So again, let's look at those resonance structures to understand why. And they're even more strong ortho-para directors than our electron donating groups through induction. So what we look at when we attack an ortho position, not only do we have that tertiary carbocation, but we also have the ability to have this extra stable resonance structure, bless you, where we have all atoms in the ring being a full octet. Versus these resonance structures, our carbocation only has 6 electrons. So that makes it even more stable. Of course, we don't have this with our CH3 group because our CH3 group doesn't have a lone pair. But our oxygen does have one. So it can donate electron density to that positive charge. Now in the meta position, just like before, the positive charge is never directly next to the carbon that has the lone pair next to it, so we don't get that extra good resonance structure. And in fact, because we can't push electron density into the ring through resonance, then the fact that this is electron withdrawing based on induction is winning because we don't have that resonance, and this is even a little bit more unstable than the CH3 meta. Because the CH3 meta is electron donating through through induction. In the para position, we see the same thing, and because the OCH3 group is fairly large, we typically get mostly para attack, but we do say this is ortho-para directed. We'll get almost no meta. Again, looking at that based on our reaction coordinate diagrams, we do see the para to be the lowest in energy, and again, that's because of sterics. The ortho is still pretty low in energy, but the meta is high in energy because we don't have that electron donating effect, and it's not having that extra stabilization. So again, if I ask you to explain this with a mechanism, I expect to see all of these things from, because you have to show the 3 different attacks to fully explain it. Because the resonance structures look different depending on the attack. So activators, all activators are going to be ortho-para directors, so let's look at some. So strong activators. These are groups that have lone pairs directly next to the ring. Now I know nitrogen and oxygen, they're all electronegative, but we have lone pairs directly next to the ring. So all of these would count as strong activators. They can readily donate electrons to the ring. Moderate activators look like these, and for most cases, the moderate activators, the way I like to explain it is, what we have is a lone pair next to the ring, so it can donate through resonance. But then we have another electronegative group next to it. And that electronegative group is pulling electron density towards it, making these lone pairs less likely to be donated into the ring. So you can think about it as if me and Taylor were racing and we technically could run the same speed, but I had someone holding the back of my shirt, I would not run as fast. So you can think about those extra electronegative groups kind of pulling the electrons closer to them, making them less likely to be donated. So they're moderate. They're less donating. We don't usually have as much of a problem with these of poly substitution, whereas these are really strong. The only exception is our OR group. That one is a little bit considered more moderate. And then, of course, our weak activating groups are our CH3R groups because they don't donate electron density into the ring. So ethos, methos, isopropyls, those sort of things are weaker. They still are para directing, they just don't have lone pairs next to the ring. So let's look at this example if we are giving the necessary reagents for the conversion. Now, a couple of things. First, I want you to know that we have a primary group here. So going through the alkylation is not going to be the best route. We'll want to do the acylation followed by a reduction. Second thing is, we haven't talked about NO2's directing ability, but we did learn that we can't do alkylation or acylation with an electron withdrawing group present. So we're going to have to put this on first. Now we will talk about the directing ability of this in the next slide, but we want this to be para to this. So what we're going to have to do is we want to add this first because it is electron donating, bless you, and it will direct to the para position. So here's our ortho meta para, and we want it directing para. So what we can do is we can do our acylation. And we want to do acylation because otherwise we would get the carbocation rearrangement to the tertiary carbocation if we did alkylation. Followed by reduction. Don't forget, for these reductions we have to have zinc, mercury, HCl, and heat. Zinc and HCl will not be strong enough to do this reduction. And that'll form this product. Once we have this product, it will be para-directing, so we can use our HNO3 and H2SO4 to add our NO2 group in the para position. Now let's talk about NO2. So let's look at NO2. NO2, fully drawn out, is a nitrogen. It has a positive charge, and then we have two oxygens. Is the NO2 group electron donating or electron withdrawing? So withdrawing. First off, remember, you don't want a carbocation next to a positively charged nitrogen. That's going to be repellent. Also, that nitrogen does not have a lone pair, so it cannot donate electron density into the ring. And nitrogen is electronegative, and then it's attached to two electronegative things. So therefore, it's going to be pretty electron withdrawing. We consider this a pretty strong electron withdrawing group, actually. So NO2 is a very strong electron withdrawing group. So it's going to actually deactivate the ring. It's pulling electron density from the ring, and therefore it's going to make the ring less likely to give up its electrons as a nucleophile. This is why we can't do alkylation or acylation with electron withdrawing groups present, because the alkylation and acylation is not electrophilic enough. With withdrawing electrons, it's going to make our intermediate less stable. Does that mean we can't do the reaction? Well, we can't do acylation and alkylation, but we can do our other reactions with it just fine. But it will be slower. And what we typically see is we have a slower reaction compared to benzene for any of these, if we're using deactivated groups first. So we're going to greatly destabilize the positive charge with that NO2 group being present, because it's going to make the positive charge less stable. So we're going to have higher activation energy compared to benzene when we're doing this reaction. As far as directing, how is that going to affect our directing ability? And the directing of these groups are going to be opposite from what we were looking at. So with directing, what we see is the same type of resonance structures. And again, our carbocation we have in the ortho position have the ability to have that positive charge in that tertiary position. But this isn't a CH3 group that's donating electron density. So in the case of NO2, now we have a positive charge, and again, remember, this is what NO2 looks like. Now we have a positive charge directly next to a positive charge. So this resonance structure is extra destabilizing in the ortho position when we have an electron withdrawing group present. In the meta position, that positive charge is never directly next to the NO2 group, so while it's still not favorable compared to unsubstituted benzene, it's going to be lower energy than our ortho attack, because remember, induction gets less of an effect the further away. So now our positive charge, it has a carbon in between the other positive charge, so it's a bit less unstable. Then in the para attack, we again see that we have that extra unstable resonance structure. So what we see with our deactivating groups is we're going to get meta attack because we don't have this extra destabilizing resonance structure where the positive charge is right next to our positive charge nitrogen, which is extra unstable. So again, if we look at this based on our reaction coordinate diagrams, now we see that the meta attack is going to be our lowest in energy. So when we have electron withdrawing groups, we're going to get the meta attack as our primary attack. So let's talk about electron withdrawing groups. Strong electron withdrawing groups contain NO2. We call this a quaternary ammonium salt. Nitrogen, when it has 4 R groups to it, has a positive charge. So nitrogen with a positive charge is going to be really strong electron withdrawing groups. So these are going to be really slow reactions. Also, if carbon has 3 halogens on it, that's 3 electronegative groups. Now, our moderate ones are the same electron withdrawing groups mostly that we talked about in the Diels-Alder reaction for our dienophile, which we needed in that reaction. So things like our carbon-oxygen double bonds, our sulfur with 2 oxygens in an R group, and our carbon-nitrogen triple bond. Now notice one thing with all of these, the atom directly attached to the benzene ring does not have a lone pair. So it can only pull electron density away based on induction. It cannot give electron density to the ring. So we don't have any lone pairs on the atoms that are directly attached to the ring. So these are meta-directors. The last one is the halogen. It is deactivating, meaning the reaction is slower with the halogen, but the halogen is actually ortho-para-directing. So even though the reaction is slower with halogenation, it can actually donate electron density into the ring because it has lone pairs. So we're going to look at that in a second. This is also why you can do acylation and alkylation with the halogen, because even though it slows down the reaction slightly, it doesn't slow it down enough to where it can't react with acylation and alkylation. But if any of these things are attached on the ring, you cannot do alkylation or acylation. Any of the meta-directors. You can do the other reactions. So let's look at the fact that even though our halogens slow down the reaction a bit, that they're still ortho-para-directors, and that's the last thing we're going to look at today. Halogens withdraw electrons by induction, but they do have a lone pair directly next to the ring, so they can donate electrons like oxygen and nitrogen can. But they're a little bit less willing to do it because in those resonance structures, the halogens have a positive charge. We still get this extra resonance structure where all the atoms are a complete octet. So this is why our halogenation is ortho-para-directing. But it does slow down the reaction a little bit because they're still electronegative. So really, I mean, the halogens are much more electronegative than oxygen and nitrogen. So that's why they do slow it down. So again, we don't have that extra resonance stabilization in the meta set. So this is just a review of all the things that I showed earlier. So it's all in one place. So with this one, the deactivating groups, we have 3. Our deactivating groups, and I'm not asking which one's ortho, para, or meta-directing, but these are our deactivating groups. Our R groups are activating. Oxygen has a lone pair, nitrogen has a lone pair, so these are activating. But these are all electron withdrawing groups. However, B and C are going to be meta-directors. A is going to be an ortho-para-director. So we're going to actually look at some examples of these in the next couple of classes and put this together. So you guys have a good weekend. It is Friday. Enjoy yourselves. I will see you on Monday. Did you say you had our test? Oh, yes, I do have your test. Hold on, let me just save the recording.